This video is on the free body diagram, among other things. So let's define what a free body diagram is. It's a visual representation of all the forces acting on an object. So individual objects or members are isolated from their environment or system, illustrating all the external forces acting on them. So what that means is you take the object you're interested in, you only concentrate on it, and you draw a picture of it, a very simplified picture of it, and you list diagrammatically, like shown here, all the forces on the object. All these arrows represent forces. So what is a force? Well, here it's defined as a straight line push or pull on an object. It's a vector quantity that has direction and magnitude. So we represent that by an arrow, and the direction is illustrated by the arrowhead. So this vector is pointing to the right, this vector is pointing up, that's the direction, and the magnitude, the size of it, is illustrated by the length of the line segment and is the amount of the push or the pull. So both of these look pretty similar in length, so the forces are approximately the same. This one might be a little larger in magnitude. Note also that direction is very important for a vector, and a vector can be defined as acting with respect to some other direction through an angle theta, as shown here. We'll do a lot of that. Okay, a moment it's a twisting effort about a point or an axis when a force is applied at a distance. It's called torque in physics. And an arc with an arrowhead acting about a point indicating direction of clockwise or counterclockwise. So basically a moment causes something to rotate. Again, moment is the same thing as torque. And a force causes an object to move in a linear direction. So the reason we're worried about both of these is that we're going to work on a bridge, and we want that bridge to hold up, so we want it to not move. So we don't want it to rotate, we don't want it to move left or right, up or down. So that's why we need to think about forces and moments. And also this free body diagram we're going to talk about more of in a moment is a way to do some bookkeeping with forces. So again, the moment review, classic example is the wrench. And so a distance d is called the moment arm, and it must be measured perpendicular to the line of action of the force. So the moment or torque about this point here where the screw is, or the nut bolt, is the product of the force you're applying perpendicular to this distance to the point here, and this is distance d. So point of rotation there, line of action there, and the distance d is the distance there. And so that's a definition of the moment, and I think we all have an intuitive idea. If you push further away from a fulcrum or a point of rotation, you're going to get a stronger force. So let's, now that we've kind of defined what a force is, you should go back and make sure that's clear in your mind. Also what a moment is, how it's defined, what it does. Recall that it causes rotation. Let's study the free body diagram. The free body diagram is an awesome tool that you may initially think, well, why do we do it? It seems like a lot of work, but after it clicks, it'll be invaluable. And every time you attack a problem in physics or engineering where you've got to deal with the forces on an object, you're probably going to make a free body diagram. So in this particular case, we have a stack of 3 books, each weighing 5 pounds, and it's sitting on the top of a table. Draw the free body diagram of the top book. It's very important that we talk about the top book here. So it's the blue one, or it's the red one, and so what we want to do is sketch the isolated object. So what's the isolated object? It's the top book. We just look at the top book by itself, and we draw it very simply. It kind of makes sense in this particular case to draw it as a rectangle as shown here, but you could draw it as a point, just a dot. Bottom line is we don't care about all the details. It's purely a conceptual practice or procedure to draw a free body diagram, so we want to remove all the things that could potentially distract us from the bottom line, which is to look at the forces on the object. Okay, so we sketch the applied and, I should say, normal forces. So when an object is in contact with and is supported by a second object, the second object can be replaced by a normal force, which is perpendicular to the surface of the second object. Boy, that's a lot of words. So let's just do that. So we've got the applied force, and we're going to obviously have that going down. That's the weight of the book. That's the applied by the Earth, I suppose. And then we've got this normal force. It's a reaction force pushing up on the book, causing it not to fall. And it's a contact force, and it's caused by the black book in the middle. If it wasn't there, if we neglected this normal force, then the weight would be unbalanced and the thing would fly toward the center of the Earth, which we know it doesn't. So the normal force, we'll use it constantly, get used to it if it's not intuitive to you. And so there we have the free body diagram of the red book. So we want to label the forces and give them names. For example, here we're calling this N for normal, W for weight. Sometimes we'll call this F sub N for force subnormal, and F sub W perhaps for force of the weight. And so there we have it. So let's see. And you can make, I wouldn't even write that there. I would just keep it completely without any sort of detail. It's just a conceptual idea. So there it is. There's your free body diagram of that red book. It lists all the forces acting on the red book and their directions and labels them. Okay. Label the dimensions. Okay. Well, this is kind of jumping ahead a little bit, but for more complex free body diagrams, proper dimensioning is required, including length, height, and angles. For example, this is a very simple truss that we'll talk about when we start to talk about truss bridges. And these blue arrows represent reaction forces of the Earth on the bridge. So in the left case here, where we have a reaction force moving up and a reaction force moving to the right on the corner of the bridge, that means the bridge is pinned down right there. And when we have a reaction force that only pushes up, which indicates that there's no reaction force of the Earth horizontally, that means it's on a roller, so it can expand if it thermally expands or contracts. And the red arrow here is the weight, and the red arrow here is, I don't know, what is that? Well, to be honest, I'm drawing a blank on what that is. It could be wind, I suppose. Okay, bottom line is that we label the angle here and here, and distances here and here. In other words, we slap on every piece of dimensioning we have. Again, this is jumping ahead a little bit, but for a free body diagram of a more complex object, then we're going to want to put all that stuff in there. So let's create a free body diagram for the sled below. What are the forces acting on the sled? We don't care about the sled. We don't care about the kitties. We don't care about the Christmas tree. We don't care about the snow. All we care about is that there's an object and we want to find the forces on them. And so we represent it by this gray disk, and we got the weight, gray square. We have the weight going down. We have a force of friction at the surface between the sled and the snow that's pulling back to the left. We've got a normal force going up, and we've got an applied force by the person that's pulling that rope. So that's our free body diagram for the sled. You can see that the normal force we can move around a little bit. Okay, now it's important that we understand the angle of that applied force, and you can see that we define it's an angle theta with respect to the horizontal. And so the image on the right is your free body diagram of that sled system. How about this guy pushing a refrigerator up a incline? So we want to find the free body diagram for the fridge only. So we identify it. It's going to stick out. We don't care about the dude. Okay, we represent it again by this completely generic thing, this square. And what are the forces acting on it? Well, it certainly has a weight. It acts at its center of mass, so we have a weight going straight down. And we're going to have other forces on here. And, yeah, the normal force. So it's going to act perpendicular to the surface. So it's perpendicular to the incline, and that's at an angle with respect to W, as you can see there. We have the guy pushing along the incline, so that's is shown there on the right. And finally we have friction, and that is shown going back the other way with respect to the applied force. And when will it appear? There it is. And again, I could put the force of friction up here. It doesn't really matter. This is purely a conceptual diagram. We put it down here just because, I don't know, it's habit, and we know friction acts at the bottom, but we could easily put it right in the middle. Again, we're just thinking about the total forces in their direction. All right. And then we plop down a coordinate system, and we say that with respect to that line, the weight is acting at an angle theta with respect to it, as shown. Okay, how about the pulley system here? I think we've studied these before. So the free body diagram of mass 1, it's very simple. We have our generic object. We have a weight 1 of mass 1, which pulls straight down, and then we have the force of tension, F sub t, pulling back, keeping it from just falling. So that's the free body diagram of mass 1. Free body diagram of the movable pulley, well, let's make it a circle just for grins. Of course, it's got weight, W2, plus the weight of the... Okay, now we're just working on the pulley, not M2, evidently. Yeah. Weight 2 plus pulley. We've got the tension coming up back that way, and so yeah, W2 plus weight of pulley. Yeah. So that, okay, that is the free body diagram on the pulley itself, not M2. Okay. Okay, free body diagram reactions. Different types of support reactions. Well, we can support things with a cable, rope, or chain. A pin, as we'll see what that is in a minute. A roller, we'll see what that is in a minute. A built-in cantilever. Again, all this stuff is specific to building things like bridges and stuff, which is what we're going to study. So to aid in completing the free body diagrams, connections are often identified with letters. So let's see what that means. So for a cable, rope, or chain, replace with a tension force only. So this is a weight supported from a cable attached to a ceiling. And this is the free body diagram. We call it T and W. T for tension, W for weight. Pretty straightforward. Again, the shape of the object is maintained, but this could easily be a dot or just a circle or a square. Doesn't have to match. So there we go. How about this sign? Well, we've got a couple cables, cable A and cable B, pulling on it. And of course, it's got its own self-weight. So it would look something like this. We've got the tension force in cable A going to the left, and the tension force in cable B going in an angle theta with respect to the horizontal, but more toward the right, upper right. And then we have the weight of the object. So from there to there, that's the free body diagram. And we just arbitrarily call cable A and cable B A and B. We could call it T sub A for tension A, and T sub B, tension B, doesn't matter. Okay, this is a pin support. So it's very specialized, and that's what we're doing. We're looking at bridges. So a pin, it's when you replace two reaction forces, one vertical, replaced with two reaction forces, one vertical, one horizontal. Basically, a pin rigidly holds that beam at point A and doesn't let it move horizontally or vertically. So we have reaction force A in the x direction, and we have, yep, as it says right there. And then we have reaction force R sub A y in the y direction. Reaction force joint or pin A in the y direction. Okay, this is a roller. It replaces one reaction force, replaced with one reaction force, perpendicular to the surface. So when we want to allow horizontal movement to allow for temperature-based expansion or contraction, we're going to put it on a roller. And in that particular case, we don't have any reaction force in the horizontal direction, so we just have the one in the y direction as shown. So when we make a free body diagram of the bridge that has this beam on it and is supported by this roller, that's the only force that we'll put on. Okay, common support reactions. Beams and truss bridges are usually supported with one pin support and one roller support. This is called a simply supported object. So create the free body diagram of this simply supported beam. This is kind of like the most primitive bridge you can imagine. It's just a beam going across a void there. There's a roller at one end, allows expansion and compression of the bridge or beam. So let's, in this particular case, we do need to maintain some similarity of the object in the free body diagram. So we have the weight. We're going to have our reaction force in the x direction at the left at point A, and also in y direction because it's pinned down there. It can't move in either direction. And in B, we just have supporting it vertically. Okay, built-in support. Built-in and a cantilever will replaced with two forces, one horizontal and vertical and one moment. Okay, here we go. So let's create a free body diagram for this one. So we've got this, it's like a diving board. It's sticking out of a wall at point A. So let's draw our beam here, and we've got this force out here. It could be somebody standing at the end of it, but that's clearly going to cause that beam to rotate. But we've got this reaction force RAX and RAY at the wall, by the wall, but on the beam, and so we write it like that. And we're going to have a moment about point A that forces it to go counterclockwise. So as I push down here, this thing is going to want to go, actually, yeah, counterclockwise. So the force here is going to force it to go counterclockwise through a moment, and to prevent this thing from rotating. Okay, summary of the support reactions. We're going to have a contact, so replace with a normal force. Cable, rope, or chain, replace with a tension force. Pin, replace with two reaction forces, one vertical and one horizontal. A roller, replace with one reaction force perpendicular to the surface. Built-in or cantilever, replace with one horizontal force, one vertical force, and one moment. So this is a truss bridge. Let's do the free body diagram for it. So we're going to draw the bridge here, and we've got the weight of 500 pounds. It acts right at the center of mass, which is as shown there. And so here we have the two reaction forces here and the one reaction force here at point C. So you have A and C, because this is a pinned end and this is a roller end. So we're going to have just the vertical. Here we've got vertical and horizontal. So to summarize, what you should have some familiarity with now is what a force is, what a moment or torque is, what, most importantly, a free body diagram is, and then there are all sorts of specific ways in which a force can be applied to an engineering object, and those were things like a pinned force, a roller force, a tension force, etc. You should be familiar with those, but the big idea is the free body diagram, and if you're a little sketchy on that, go back, take a look at some of the slides, and then we'll discuss it in class. Thanks for watching.